My name is Megan Mishra, and today I'll be discussing the 4th Physics 2211 lab on oscillations. To start, the main purpose of the lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We'll do this through comparing the predicted and observed motion of the mass, and by plotting energy changes observed in the model and determining if it satisfies the energy principle. For a preview of the results, we'll find that the total energy is always equal to 0 joules, and that the gravitational potential energy and spring potential energy are opposite of one another. One of the two main physics principles for this lab is Newton's second law, or the momentum principle, which states that the force that acts on the system from the surroundings results in changes with momentum. We can see the equation for it here, and in our case specifically, we know that the net force will be equivalent to the spring force plus the gravitational force. So the magnitude of the net force is equal to Ks plus mg, where K is the spring constant, S is the distance, m is the object's mass, and g is gravity, or 9.8 meters per second squared. We can also derive the velocity and position update formulas from this, which will then be used in the GlowScript code. The second main principle is the energy principle, which states that energy is neither created nor destroyed, but can be transformed or transferred. The total energy of the universe is constant. It can be represented as the change in energy being equal to the work done on the system by the surroundings plus the energy due to heat. In our case, there is no Q, and the system is the mass, spring, and earth, so the surroundings, which is everything else, has no effect as no work is being done. Because of this, there's no energy change, meaning that total energy is 0. Energy can also be represented as the sum of kinetic and potential energy, so in our case this leads to saying that total energy is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy, which is all equal to 0. The individual equations for kinetic and both types of potential energy can be seen here. For the analysis of experimental data, Tracker was used. Using the provided video of a spring oscillating in 2 dimensions, x and y, a coordinate system and a calibration stick were applied. We were told in the lab's instructions to use the values given to us in pre-lecture video 52, so the calibration stick length was set to 0.7 meters long, and the mass was then tracked frame by frame, producing the 2 position versus time graphs for x and y on the right. Next, it was necessary to make a computational model using GlowScript. For the initial conditions, the system's mass was again taken from the pre-lecture video and was equal to 0.402 meters. The initial position was taken from Tracker, as seen here, and the initial velocity is 0.000 meters per second as the mass spring system starts at rest. The initial time t was 0, and delta t was chosen as a small number that is an integer multiple of the time interval between frames of the experimental video. The gravitational constant is always 9.8 meters per second squared, and both the spring constant and the relaxed length of the spring were given in the pre-lecture video. S, or distance, was then calculated, and the equations for both kinetic and both types of potential energy were also calculated. Adding these values together gives us total energy. In the while loop, the gravitational forces were calculated, then the spring force, then both were added together to give net force. The velocity and position update formulas were then used to find the object's velocity and position, and then the spring was updated. Finally, the energy changes were found. The code gives us this model of the change in energy of the system versus time. Here we can see that the change in gravitational potential energy is always directly opposite the change in spring potential energy, as in, when one is at max, the other is at its minimum, and vice versa. The total energy, as seen in orange, is consistently 0. Uploading a CSV file of the experimental data from Tracker allows the code to compare the observed data versus the computational model's position versus time in both the x and y components, wherein the model is in blue and the experimental values are in red. We can see that both directions have some discrepancy, although they're fairly similar, with the x component only showing that the experimental data is slightly shifted left as compared to the model, and the minimums and maximums of the y position are a little smaller in the experimental results. For the y component specifically, this difference between observed and model increases over time, so there's some error. Some sources of this error could be that drag wasn't taken into account, so including a drag component could increase the accuracy going forward. In conclusion, looking at what all this means, we can see that our model of the spring mass system does in fact satisfy the energy principle. We know that theoretically the surroundings don't affect the system and there's no work being done, so the total energy should remain constant as 0. As we can see from the modeled graph of change in energy versus time, where the total energy is represented in orange, the orange line remains 0 over the time interval, so our model does in fact satisfy the energy principle. In addition, we can provide 2 estimates for oscillation periods. There is a formula for calculating this, but since the oscillation period is simply the time it takes for a spring to complete one complete oscillation, or the time it takes to return to its initial position, we can just use the graphs found through Tracker. For the x component, the spring mass system starts at negative 0.107 meters at 2.089 seconds and returns to this position again approximately at 3.704 seconds. So the period of oscillation found by subtracting the two is 1.615 seconds. The same process is done by the y component to give us a period of oscillation of 1.520 seconds. The x component is longer as the forces acting in the x direction are smaller in magnitude. Thank you.